In today's class, we are going to have a very important thing, that how can just relate observables with the Hilbert space we have defined as such. So it's a very important step in how we can just have a correspondence to the observables with how we have constructed a Hilbert space. So that's an important step in how we can formulate or formalize observables in our quantum mechanical understanding. So this is the important thing. From the second postulate of quantum mechanics, what we are going to see from second postulate of quantum mechanics, observables like observables uh, can be position, then there can be momentum, and they can be energy and other things, energy, etc. etc. So the point is that we normally have an Hermitian operator, which is associated with the observable. In a sense, once we have an operator, it's operating on a Hilbert space and towards the Hilbert space. So it's operating an Hermitian operator. So you can say that these operators are, for example, they are Hermitian operators. They are represented in an Hilbert space, and whether these Hermitian operators are linear, they are linear or and self-adjoint, uh, and operators in general, and linear operators in particular, because linear operators also previously also said they are very much important in how we formalize this property, linearity property, becomes very much important in quantum mechanics. So linear property, they are the property of they are related as if they are adjoints of the operators. So if we sum up in one sentence, an operator is a map. So if I map of Hilbert space on its own self or space or self or space. So if I follow, so in a sense, if you operate on a given function, but that's operating in that's part of Hilbert space. So one part of Hilbert space is related with some. You can say it's a mapping of Hilbert space on itself. So an operator A takes any vector psi in Hilbert space to another vector A psi. So an operator A, it acts on this psi in Hilbert space, takes any vector A psi which is denoted by A psi. So A acts on psi, it will take it to A psi. So that's it. And product of two operators are defined if that so we can say that product of two operators a b psi. So you have to see this psi is the sort of wave functions which is we have defined previously also. It's a wave function in that sense. So it's a wave function which was previously we also identified it as a state of a given system, quantum mechanical state. And in this class, we are seeing how observables can be related with operators and how they are related with states. So the states, so they can have this two operators. They are acting on this state, so they should have. So it should not change anything. Like if first this product of two operating on this, so it's like this. So we are using complex numbers throughout we have used the property of Hermitian conjugate in how we define the norm inner product spaces, which has a property of being symmetric conjugate. The norm being positive definite. So the notion of complex thing comes into consideration. So any ordinary complex number can alpha, any ordinary complex number alpha can also be regarded as an operator that multiplies a state vector by this thing. So if you just use the numbering the equation on the book, so you can say it like this. So you can say alpha is an operator on an arbitrary state vector with a. So you can again have this property. So you can have this thing acting on psi should give us alpha. So it should not matter. So this is it. So where alpha is an ordinary complex number. So you can have this property can be similarly seen to be attached to it. Now we can have, for example, again we can enumerate some of the properties. For example, one of the property is, for example, if two operators A and B are defined as an operator, then which are acting on state vector psi, then sum of two operators, so A plus B of psi should be, we have been doing it throughout, so this property should also hold. As A acting on psi and B acting on psi, this property of this thing should hold, and this will be the property of. And other properties like that of, for example, other properties like if you have a zero operator which is operating on psi, so it will be give zero, or commutativity. If it is an arbitrary operator, then it will be 0. And from this you can say 0 is 0, 0 plus A is, so A is an arbitrary operator, it will give you A alpha into 0. So the commutative order should not matter. If you change the order, it will give you 0. And the identity operator can be defined as I. Identity operator will give the state function back. That's it. Or for an arbitrary operator, an identity operator acting on arbitrary operator should give that commutative should also hold here, and it will give operator back. And linear operator, A is one for which A of psi plus psi prime should be equal to A of psi plus A of psi prime, and A of alpha psi should be equivalent to alpha times A psi. So you can see here also this scalar is operating on this function first, then the operator is acting on whatever has been there. So the thing is, it doesn't matter whether you operate these two separately. So the thing is, they were enumerating these properties here. And further, for example, further so for arbitrary state vectors, arbitrary state vectors sin psi prime and arbitrary number alpha, so it's easy to see that if A and B are linear, then so are AB, and for alpha A plus beta B for any numbers alpha and beta, and also for 0 and 1, both are linear. For arbitrary state vector sin psi prime and arbitrary numbers, so we can have two numbers alpha and beta, A and B are linear. So if A and B are linear, so are alpha and so two scalars multiplying these as, so they can also be linear. So once, how can you translate this thing here? So now adjoint of an operator is defined as, so now you are coming normally in quantum mechanics, we normally talk of properties of self-adjoint operator. An operator having a property of being self-adjoint. So before we talk of self-adjoint operator, we will straight away say that the adjoint or a dagger of any operator. So here we are defining the sense in the general sense. An operator may be linear or not. Linear or not is defined as an operator for which these properties should hold. Property is psi of A dagger psi should, if you just shift it here, it will be A psi sorry, it is A dagger E. If you just if we put it some connection here, it will give psi prime. You can, if you change here, you can do it like this, psi dagger, psi star. Sorry. So if it comes here, the A dagger will come out to be A psi. So A dagger will be A, this psi will be psi prime, and psi it will come back. So you can write it like this. Now this is better. This is fine. So in the same way, we can write psi prime A dagger psi is equal to psi. This is A psi prime star for any two state vectors, for any two state vectors psi and psi prime. So what you are going to say is that so it's elementary to show that AB dagger is equal to B dagger A dagger. So you can have simply you have these operators. If A B dagger, so if you just it's A B dagger whole, it should be equal to B dagger. So you can verify this property in a very simple sense. And other properties you might be knowing it throughout is conjugate, self conjugate, and the conjugates of itself include the operator back. And the other property is that if you have a scalar conjugate operator, the scalar will come back. So A transpose will give you A transpose. So if it's a complex thing, then it will be conjugate. If it's not complex, then you can see it can be alpha. And A plus B dagger will be equivalent to A dagger plus B dagger. So these are the properties. Now we are coming to what we have been doing yesterday. So we have so if you introduce if you remember, if you introduce the thing that yesterday we defined psi, the components of psi in terms of phi j, you can write it like this, and psi can be written as. So first, let me say that if we introduce complete orthonormal set of basis vectors phi I. So we can represent any linear operator A by the matrix Aij can be written as. So if we introduce complete orthonormal set, so orthonormal set, the condition, orthonormality condition of basis vectors, it has both the conditionalities there in orthonormal set of basis vectors phi. So if you want to write it in terms of this Aij, if you don't want to write it in terms of matrix components I and j, you can see it's an inner product of phi I and A times phi j. So you can write it like this: phi I inner product of phi I phi j, its scalar can be taken outside. So if it's AI, so that will be Aij, if it's in that sense. But if you remember, we have been seeing the wave function psi. If you want to write it in terms of component, psi can be written in terms of components. So you can say phi j psi into phi j. So what should be so what we are going to do is that the matrix representing operator product AB is the product of matrices, such that A, B, I of J. So I, J may be rows and columns, you can see it. You can write it in terms of phi I. So again, the way we have an operator here, it's not one operator, it's two operators, A, B with indices I and J. So phi A, here the property will be, it will not be A, it will be A, B, phi J. Again, we can write it as, so you can have, you can write it as, further, if you want to write it in terms of K, you can have phi I, A phi K, this is one, and phi K, A phi J, sorry, B phi J. So you can see it, this and this. So it will be A phi ij, B phi kj, B phi kj. So you can write this in terms of k. So it will be 8 terms of. So we have written I and j in terms of. We have also introduced a third thing called k, so that this can be written in terms of aik and bkj. Bkj. So this is the way we have written in terms of how we can write operator product of two matrices can be written in terms of components. So you can write it like this. Now what we are going to say. So we frequently encounter complete set of state vectors phi zeta. So phi zeta labeled with. So we have been talking of in previous class continuum variable zeta instead of discrete variable iota. The orthonormal set or continuum variable is phi zeta prime. Is again it's zeta minus zeta prime for the orthonormality condition. If zeta is equal to zeta prime, it will be 1, or if zeta is not equal to zeta prime, it's 0 for the orthonormality condition. And in case we have an operator which is acting on zeta, if we have operator, so that operator can be defined as so we are going to use this property, it's phi prime zeta and a phi zeta. So this property what they using here. Now if you want to instead of equation this, so now if you want to use this instead of this, because there are two labels, so if you want to write it in terms of this, so we can write, and if you want to see the integral of this thing in some integral form spanning a certain space, so we can say we can have zeta is a zeta zeta, b zeta zeta prime. So it will be d. So it will be a zeta zeta prime, b zeta zeta prime, and it will be d zeta now prime. So now the adjoint of the operator, which is represented by the transposed conjugate complex such that AJI dagger will be equal to AIJ. So again, so let me do it here. So we are basically doing nothing. We are enumerating the properties of these adjoint operators in all this component form. So because the notion of operator and how we relate operators in observables, and whether it's an operator or self-adjoint operator in a Hilbert space, so this mathematical language comes throughout in the edifies of the mathematical wavelet and how the representational part of quantum mechanical observables or variables or parameters or whatever, how the way we formulate. So the algebra part of it becomes very much. So we have to go through this very exercise. No, it's not that painful. You might enjoy it after a bit of practice or being familiar with it. But in the first place, it might look, you might get stuck. And that may not be that interesting. But now the thing is that the adjoint of the operator, is represented by the uh, transposed complex conjugate of the matrices, conjugate of matrix. So A dagger Ij will be equivalent to Ai Ag I star. That's it. Now we are coming to the second postulate of the quantum mechanics. So what the second postulate of the quantum mechanics states that so the second postulate of quantum mechanics is second postulate quantum mechanics holds for a state that has a definite value A holds for a state that has a definite value A for an observer represented by linear Hermitian operator A if and only if the state vector psi is an eigenstate of A with eigenvalue A. So second portion of quantum mechanics states that holds for a state A if the observer represented by the linear Hermitian operator A, if and only if, so this condition becomes very much restrictive. It will only hold. So for a state, an observer is represented by Hermitian operator if and only. It can only be represented by Hermitian operator A if and only if. So this is a restrictive condition. Only if the state vector psi is an eigenstate of A with eigenvalues A in the sense that A psi is equivalent to A psi. So the thing is that for an observer represented by linear Hermitian operator, so for a state, an observer represented by linear Hermitian, a state can be represented by linear Hermitian operator only when the state vector psi is an eigenstate of A with eigenvalue A. So eigenvalue, this is eigenstate of A, it will be this. So this condition should hold necessarily for an observer to be represented by the linear Hermitian operator. So this eigenstate of A should be an eigenvalue of A. So this is a very restrictive condition, which will come by and by how things such that. So this is in the mathematical sense we are saying that this condition should hold if at all state of an observer is to be represented by linear Hermitian operator. That eigenstate of A should be the eigenvalue of A. So that's it. And also if a psi prime is a prime psi prime, then because A is Hermitian. So this is another. So it will follow this thing. So if you just if it's A psi prime, so it will be A prime psi prime. You can see it because A is, if it's Hermitian, for Hermitian Hermiticity, this will can hold, this condition hold. And other properties also which we have been without doing. So if you have a scalar which is outside, so we can have it's represented by, you can shift this thing. You can write it as psi a prime psi is equal to, is an operator. So this is a psi prime psi. Now if it's a is it's replaced by a, so it will be a psi psi prime psi. So these are different ways we are writing. Provided provided that from this we can say, provided that psi is equivalent to psi naught is not equal to 0. This is one condition, and a prime is equivalent to a. And for a prime not equivalent to a, psi, this inner product of psi with psi prime is 0. So for one condition, if psi is not equal to psi prime is not equivalent to 0, then it is. So if it's not equivalent to a prime, so this inner product will come out to be 0. So this is the allowed values of observables or real and state vectors with different values for any observables or orthogonal, or the orthogonality condition is given here, it's sort of orthogonality conditions. Yes. So in terms of, if you want to write it in terms of matrices, if you remember matrices, for example, if you just as a mnemonics wrote aij in terms of phi I a phi j, and a zeta prime is phi zeta prime a phi zeta. So now we are going to translate here. Here we are going to translate it in terms of this thing. Then write it here. Then sigma of aij phi j psi is equal to, so a should be equal to this. So it will be a times phi I psi. Or else you can say integral of a d zeta, a zeta prime zeta phi zeta psi will be a times psi zeta psi. So the Hermitian operators, now I'll write it. So the Hermitian operators, so the Hermitian operators, so this is this thing, or the Hermitian operators which represent these observables, which we have said have an important properties. Important property is that their eigenvectors for complete sets. So this is an automatic for Hermitian operators acting on the space which might be having finite dimensionality. So even though the property, we have constructed a Hilbert space in a sense of defining a Hilbert space from a sort of finite dimensional space with some modulo subconditions. But in principle, we can Hilbert space is an infinite dimensional vector space. So, but for this, so it may be the property may be difficult to prove for the infinite dimensional. And that Hermitian operators may be infinite dimensional space having this property of that eigenvectors are complete sets or complete sets. So finite dimensional cases you can easily prove it. For infinite dimensional spaces or Hilbert space in the proper defining the proper sense, it may be a bit exercise which we are looking to prove that whether eigenvectors or complete sets or not. So if psi r be a complete orthonormal set of state vectors representing the states with values ar of the observable represented by the operator a for which this condition holds that way. So if you want to find out the observable which is normalized over a given wave function psi and weighted by each probability, so what can be the total you can say expectation value in that sense of this thing, the relative weights of the probabilities that control. So I'm using these words which might not carry sense because you should have knowledge of probability and stats, how we average out observables in a given sample. So that understanding is how we define expectation values. Here we are trying to see these states, how they are to be represented, and if we just can say the probability, the expectation value A of psi, which is a part of this state, this psi. So it's given by the inner product of it, it's psi r psi square is, you can write it as psi of E psi r or psi r psi can be written as, so you can see this psi r, it's repeated, you can write it as psi of psi, psi of A psi, sorry, psi of E psi r, it's fine. And if you again you can just move this, you can just if an observer is observable which is represented by the operator A which is acting on some wave function in a successive way, this scalar also should accordingly, you can just this has an this thing here, if it's n, 2 is 3, so you can have this representation here for any series. And more generally, we can define vectors, functions of Hermitian operators specifying for any arbitrary linear combinations. So we cannot have a arbitrary linear combinations. The way we define arbitrary operators. So arbitrary linear combination means CR, psi of R can take any values of a complete independent set of vectors psi R with the values. So we can have f of A sigma r, CR psi r can be like this AR psi R. So in general, we can say the expectation values of the function of an operator is not equivalent to the function of the expectation values. So the thing is that if we define, this means that f of a psi, a into psi is not equivalent to f of a psi. So function of the operator is not equal to the function of the expectation value. So function of the operator is not equivalent to the function of the expectation value we are getting. So these it may not it's not equivalent to this. So what we have to do with this thing is that and in fact for Hermitian operators normally a square psi is greater than a psi square. Square of the function is always greater than the square of the expectation value of the operator. Or square of any Hermitian operator B square psi can be written as inner product of B psi. So what do we have all to do it? We are coming to use these identities in the next class, how we can represent the uncertainty principle, generalized version of uncertainty principle, and where we're trying to make a ground of these properties. How the expectation value of an operator is not equivalent to the expectation value of the given of the operator of function is not equal to the expectation value of the operator, and these properties such that if you want to write it, for example, you can write it if I'm just using following the book, or you can see any book on statistics. So so here the only thing is that we are defining expectation. The variables here are how these operators acting on these wave functions. What's the value we are getting? So it's one thing. So it's exactly, you can write it this. You can have a square minus twice a psi square. One will just get subtracted. You can also write it like this: psi square plus a psi square. Or you can minus twice a square minus, it will be a square psi. So it's square of the operator, square of the expectation value of the operator, the difference of the two. As this shows, a psi square is at most equivalent to this thing. Only if, so this is equivalent to this only, so this is an important result. If psi is an eigenstate of A. So we have reached to this equation. Now this understanding, taking this understanding, we are going to just move forward. How we can state generalized uncertainty principle, and we can, the way we had used these Shiva's identities previously also, and using those things we can carry forward our mathematical understanding of how mathematical formulation of quantum mechanics or clothing of quantum mechanical observables in the mathematical language of vector spaces or input spaces.